Hello. I hope you guys are enjoying hypothesis testing, as that's all we're doing for the next 2 weeks. So we're back again in the barn, and this time we're doing hypothesis testing for standard deviation. Up to this point, we've looked at the mean and we've looked at proportion. Those are the two variables that we have studied frequently throughout the whole class. But now that we're getting into this, there are some other things that we can study. And one of them is standard deviation. Now, when you do a mean problem, when you're doing an average problem, the standard deviation is always kind of there in the background. It always comes along for the ride, but we're actually not studying the standard deviation in those problems. So now we want to study the standard deviation. And here's the thing. Why, when, what's the deal with standard deviation? So remember that standard deviation means how does your data vary over the number line? How does it spread out over the number line? And the people that care about this in particular are people that are doing very technical things. So example, engineers are very interested in standard deviation. Manufacturing is very interested in standard deviation. And so as an example, and again, these are just, I'm not an engineer, I don't work in a factory, so these are just examples that I'm giving you in a layperson's point of view. But let's say that you were to work in a factory that created bolts, okay? So you are in the bolt factory, and across the street is the nut factory. I don't know why you guys don't do both, but the nut factory is over there, the bolt factory is over here. You work in the bolt factory, and your job is to create bolts. So the machine, gets the metal, shapes the metal, does all of that work for you. But as the machine works day after day, the machine might get a little bit dirty, or maybe gets a little bit corroded. And so what starts to happen is the machine is making bolts that are supposed to be a certain size, but they're not all exactly the same. Now again, we're in statistics, so nothing is ever 100%. So every bolt that comes out of the machine is going to be a teeny bit different than the last bolt. They're all going to vary. Standard deviation, how do they deviate or vary? So when those bolts come out, they vary a little bit, and that's okay, that's the way life goes. Okay. Now, over at the nut factory, your friend makes the nuts to screw onto the bolts. Okay, so we got the nuts and the bolts. And over at the nut factory, he's doing the same thing, and he's making the nuts, and they're coming out of the machine. The metal's getting melted and shaped and everything. And every nut that comes out is not exactly the same. Okay? That's all right. That's okay. But in the end, when we've got all the bolts and all the nuts, what needs to happen is when you take the nut, it needs to screw on to the bolt, right? That's how nuts and bolts work. The nut has to screw on and hold tight. So if those nuts and bolts, if they vary too much, it could be that you go to take the nut and screw it on the bolt, but it doesn't fit. It doesn't fit because the size has varied just a little bit too much. Or other situation, you take the bolt, you go to put the nut on, and it's not tight at all, okay? And so if that's the situation, obviously the nut and bolt aren't gonna work. Well, either situation, the nut and bolt aren't gonna work. Now, those obviously would be drastic, that they don't go together at all. But normally what might happen is they go together, but they don't fit tight because they deviate a little bit too much. They can deviate a little bit, but not too much. Now, you might be going, who the hell cares about the nut and bolt factories? But every one of us cares about the nut and bolt factories. Have you ever driven across a metal bridge? Guess what holds metal bridges together? Nuts and bolts. And we're talking like the big, massive nuts and bolts. Okay, if you don't like the bridge example and you like amusement parks, think about roller coasters. What holds roller coasters together? Nuts and bolts. And every time a car goes over that bridge or a roller coaster goes over the track, everything shakes a little bit, okay? Everything shakes a little bit. And if the nut and the bolt are where they should be, when they shake, nothing should happen. They should be good to go. But if the size or the shape of the nut and the bolt deviate or vary too much, when a car drives over that bridge and the nut and the bolt shake, that nut loosens up a little bit. And then the next car drives over and the nut loosens up a little bit. And then the next car and the next car, you see where I'm going with this? The more the bridge shakes every time, because things are not tight, that nut is loosening up until it finally comes off. Okay? Now, you know, there are backups in place, either on your bridge or on your roller coaster, so it's not just one nut and bolt that are holding up the whole bridge. But imagine if those nuts and bolts vary too much, if the standard deviation is not kept where it needs to be, okay, we're going to have some big problems. So again, if you're into engineering, you understand that nothing is ever going to be perfect because we're in the real world. So it's not going to be perfect, but you need for every nut and bolt to be within a certain standard deviation. We cannot have them vary in size or shape just all over the place. They have to fit together so that the whole project fits together. And again, it's not just nuts and bolts. Like it's anything that you engineer when you're cutting a piece of wood to build a building. Every time you cut a piece of wood, let's say you need these pieces of wood to be 10 feet. Well, every time you cut it, is it exactly 10 feet? Or is one a teeny over, another a teeny above? The idea is they're not perfect, but they can't deviate too much. So again, like I said, very technical, a lot of manufacturing problems. As another example that's not serious really in the scheme of the world, but potato chip bags. They say, you know, like there are 16 ounces of potato chips in there. Well, when you open up your bag, if you lucked out and got 18 ounces of potato chips, well, you're like, woohoo! But if the company is mistakenly putting too much potato chips in each bag, eventually they're gonna start losing money. And on the flip side, if you open up your bag and you're like, it's half empty, you're gonna be kind of pissed. So the idea is when they say that there are 16 ounces of potato chips in a bag, is it gonna be exact? No. Is it gonna be close? It better be, otherwise problems are gonna occur. So that's what we're looking at here when we talk about standard deviation. Now, when the data is normal, we know that that means that the mean has a bell-shaped curve, but that's not what we're interested in here. So when the data is normal, we will see that the graph of the sample standard deviations is right skewed. And the graph actually looks like this. All right, so the data is normal, but we're not talking about the mean. The mean would most definitely have a bell-shaped curve. We're talking about the standard deviation. So when the data is normal, the standard deviation should look like this. The graph of this sample standard deviations, I guess, is right skewed. So this being 0 and that being bigger and bigger and bigger, what did we just say? We want our standard deviation to be small. We want things to vary as little as possible. So do we want those standard deviations to be closer to 0? Yes. And that means that the bars need to be to the right where 0 is. So 0 is on this side, and then the standard deviations will peter out as they get large. We don't want the large ones. We want them to clump closer to 0. Okay? Now, this is a new graph for us. It says the data is normal, but this is definitely not the bell-shaped curve. So we're not dealing with z-scores here. We're not dealing with t-scores here. This is a new graph. And this guy is called the chi-square distribution. Okay, so I'm going to label it there. Chi, the Greek letter chi, looks like a capital X with a curly Q on it, not just being cutesy. It has that little kind of tail like that. So this is called the chi-square distribution. Okay, when you see it in the book spelled out, it looks like chi, okay? So that's how we say chi. So, you know, if you say chi, I mean, there's nothing wrong with it, but if you're like, what the hell, she's saying chi and it's chi. No, it's chi. So that's chi-square distribution. And the chi-square distribution will always, 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 always be right skewed. So always right skewed. With 0 at the left, okay? So 0 will always start us off at the left, and then we will have a right skewed graph. Okay, now, because we're dealing with a different graph here, that means that we're going to be dealing with, we can't do a z-score, we can't do a t-score, we can't use the easy peasy z-score. We're out of, you know, we're out of that realm. So we need a new test statistic. So our new test statistic is going to be a chi-square score. Okay, a chi-square score. So not a z-score or a t-score. And the chi-square formula, this chi-square score formula, it's not that bad actually. It's n minus 1 times s squared over sigma squared. Now remember, we're studying standard deviation, so no P's and Q's, no means going on here, only standard deviation, so we've got sigmas and s's running around, okay? So that's why those guys are there. Now something to keep in mind, when we've been doing the number of examples using the normal curve, our z-scores always seem to stay between like -3 and +3, that's kind of the norm. These guys can get super large, okay, so they can get very large. So it is not uncommon to fiddle out this formula and end up with a chi-square score of 52.658. Okay, so definitely can get large on this one. Now, before we do any examples, let's just use our calculator a couple times to make sure that we can find the area that we need, because just like we've done in the other examples, we're going to be looking at tails, you know, so we're going to be doing that and then like making a tail. So we got to be able to do that, and because it's a different graph, things are a little bit different. Not too bad, just a little bit.